Vietnam culture, we have 4 cuts.
No, Africans live
And
in
then we
this.
start with the patch. There are pizza with patch with Schnider. He's not from Pakistan.
All right, thank you all. My name is Patrick, I'm from Syria. And you can use it as a follow-up to the pizza that we got for lunch. This is now kind of the theoretical background of how we would have been supposed to share this. So imagine that you have a pizza, which consists of a pizza bread, some tomatoes, some cheese, and some olives. So you have 4 ingredients. And you also have a friend. And you want to share this pizza. And you want to share this in a fair way. So you both want to get exactly the same amount of bread, the same amount of tomatoes, the same amount of cheese, and the same amount of olives. So here are 2 examples how this could look. So we have this bread here, and then you could slice, make 2 cuts here and here. One person will get these green slices, one person will get these blue slices, and you can check that in the sum of these both slices, both people will get the same amount of bread, the same amount of cheese, so the same amount for each ingredient. You could do so using only 2 cuts. This is another option for a different pizza where you actually cut parallel, and also here you can check that one person, so in which case these 2 blue parts, gets the same amount of each ingredient as the one person getting this green part. So in more general framework, we are given 4 mass distributions in a 2-dimensional space, and we want to simultaneously bisect these mass distributions using only 2 lines. And then again, with these 2 lines, you will have these antipodal regions, or these regions if they are parallel. And in these regions, we want exactly half of each of these masses. So this is very related to the very famous ham sandwich theorem that I guess most of you know, which says that if we have d mass distributions in d-dimensional space, then we can simultaneously bisect them using 1 straight cut, so 1 hyperplane. So in 2 dimensions, this means if we only have a pizza with 2 ingredients, so a rather boring pizza, but if we only have 2 ingredients, then we can just cut this once, and we will be able to split this evenly. Of course, as computational geometers, we're also interested in discrete versions, so these whole things work for point set, and all the results that I'm going to present, even though I present them in the more general framework of mass distributions, they all also work for point sets. All right, so let me recall a proof for the ham sandwich theorem using a topological argument, and a topological theorem called the Borsuk-Ulam Theorem. So this theorem from the 1930s says that if we have some continuous mapping from the d-dimensional sphere to the d-dimensional space, then there are 2 antipodal points that have the same value. So what does that mean? Let's think about the 2-dimensional sphere. So you have some kind of a ball in your hand. Then you crunch this ball until it is flat. And you can put it into the plane, which is the 2-dimensional plane. And then there will be 2 antipodal points on this ball that are going to lie on the same point on your plane. No matter how you crunch it, this will always exist. And there's also an equivalent way to phrase this, that if we have a so-called antipodal mapping, which is a continuous mapping such that any 2 antipodal points have the respective negative values. So if a point has value k, then its antipodal point is going to get assigned value minus k. Then this function does have a 0. And it's easy to see how this follows from the original theorem. They're actually equivalent, but that's not so important here. And using this result, there is a very neat proof for the for the ham sandwich theorem, because we can view every line in 2 dimensions as, or every half plane in 2 dimensions, we can associate to a point on the sphere just by this formula. So if we look at the half plane defined by u1, x1 plus and so on to ud, xd larger or equal than u0, this gives us d plus 1 coefficients, so u0, u1 up to ud. And this we can view by normalizing. We can view this as a point on the d-dimensional sphere embedded into d plus 1 dimensional space. And like this, we can then find if the positive half plane of that, and just take the negative half plane also by switching the sign. And the property that we have here is that all the things these movements that we can have are pretty nice and continuous. So if we just move this point on the sphere slightly, also the directed line that is associated with that moves in a continuous fashion. And the other nice property is that if we look at the antipodal point, this gives us exactly the same, but just oriented in the other way. So the plus and the minus just changes. This is easy to see because if you just plug a minus in front of all these things, then it's just the same as just switching this sign. Okay? So what we can now do is, well, just for each mass distribution that we have, and for each point on the sphere, we just take the mass that lies in the positive half plane, defined by this half plane up here, minus the part in the negative one. And this is going to give us d different functions, all of them just a real number. And this is nice, continuous, and it's also antipodal. So we know that there is some point on the sphere where all of these functions are 0, but all of these functions being 0 just means that, well, the positive part is exactly the same as the negative part, so that exactly half of the mass is going to lie in the positive and in the negative half plane, respectively. So that's a very neat proof. And this actually generalizes to arbitrary algebraic surfaces. So now, if we don't enforce degree 1, which is a hyperplane, but we can have any degree, you can do the exact same thing and actually get more functions. So it's just the same idea. You now have more coefficients, but you can again view this as a point on this now higher dimensional sphere. And again, it's nice and continuous, and antipodal points are just going to be the reversal of this half plane. So the same argument holds for any algebraic surface of a certain degree, and you can get quite a few masses that way. And so, for example, one problem would be that if we look at dimension 2 and we look at the conic sections, which are algebraic surfaces of degree 2, then if we plug in the numbers, we can actually see that we can simultaneously bisect 5 mass distributions. Okay, so, but now we want to have 2 lines. But actually, 2 lines are a conic section. Just a very degenerate one, but when can a conic section be 2 lines? Well, it's just kind of at the boundary there when so a hyperbola changes its focus, or then when at the point where a hyperbola changes to an ellipsoid. And we actually get, as a degenerate case, 2 lines as a conic section. And the nice thing is that for conic sections, we actually have a beautiful condition to find out when it's actually degenerate. So there's this determinant of some matrix, and a conic section is degenerate if and only if this determinant vanishes. Now, the determinant is, as we know, a continuous function, and since it's a 3 by 3 determinant, if we plug a minus in front of every entry, it's also going to get a minus sign before the determinant, so it's also antipodal. And now this means that we can do the same thing as we did before with this polynomial time sandwich cut, but we only use 4 functions to split our masses, and for the last function, we just plug in this determinant. This is again a continuous and antipodal function. So by Borsuk-Ulam, we know that there is some point on the sphere where all the functions are 0. So that means we have found a conic section which simultaneously bisects our 4 masses, and that is degenerate by this last condition. And there's several options how a conic section can be degenerate. Either it's two lines, in which case we are happy, or it might be empty or a single point. But in all of these cases, we are certainly not going to have simultaneously bisected all our masses, because the whole mass lies in one of these parts. So the only options where we can actually have bisected these masses are if it's two lines. And this shows that what I claimed, that the four mass distributions can actually always be bisected by two lines, which might be parallel or crossing. This we cannot say. Good. So what would be a generalization of that to higher dimensions? So now, if we consider n times d mass distributions in d dimensions, question is, can we bisect them using n hyperplanes? So this would be, if you think about this for one hyperplane, this would just mean that d mass distributions can be bisected over one hyperplane. This we know that that's true, because that's just the Ham-Sandwich theorem. Now, what do I actually mean by simultaneously bisect? If we have n hyperplanes, we can get this kind of checkboard title here. And then again, half of the mass would lie in this green part and half of the mass in this blue part. If you want to have this a bit more formal, you could imagine all of these being directed, and then you have a positive half plane and a negative half plane for each of those. And then, for example, the blue part would just be the points that lie in the positive part of an even number of these planes, and vice versa, so just this timing. If you think about the same thing for dimension 1, this is just the so-called necklace splitting problem. So where you have a bunch of points or pearls on a necklace, and you want to split them using as few cuts as possible. And this is exactly this statement up here for equals 1 in one dimension. Well, one approach how we could prove this would be to see that n hyperplanes are just a very, very degenerate algebraic surface of degree n. And actually, by this polynomial Ham-Sandwich theorem, we actually have quite a lot of freedom to enforce these degeneracies. So if we can somehow use these n plus d, choose d minus 1 minus n times d functions to enforce that we really have a very degenerate algebraic surface of degree n, we would be done. The problem is that there are some known conditions to enforce these degeneracies, but the ones that we found are either far too many or they're not antipodal. So we cannot use them yet. But if you know of anything in this direction, I would be very interested. But using some arguments like that, we were able to show that in 3 dimensions, we can at least do 5 mass distributions using 2 planes. So that's not exactly this thing up there. There we would hope for 6, but we can do 5, which is already better than the 4 that we have in 2 dimensions. Yeah, so for the open problems, of course, the general case, are there such antipodal conditions, and few of them, such that we can enforce these degeneracies? If we can find those, we can prove the general case. Are there different approaches to prove the general case? So are there some different versions of the Borsuk-Ulam Theorem that we might be able to use? And we're actually looking into this. It's not yet completely written up, but we have some promising results that might generalize this to at least even dimensions. And the algorithmic part is still widely open. So we now know that there always are 2 lines that simultaneously bisect mass distributions or point sets. But how can we efficiently find these lines? Just a naive approach will be trying out all combinations, which will be like n to the 4 different combinations, using some nice data structures. We might not have to count the points each time, but are there algorithms that do significantly faster than n to the 4? So is there something better than just trying out all possibilities? And this is also an interesting problem. All right. Do I still have time?
Yes.
Okay, so let me skip that and go to some chronology. So this general idea of using antipodal functions to enforce some other conditions on the space, we could also use to actually enforce some other conditions like two lines, but one line should be parallel to a given line. So for one of the lines, you wanted to fix the direction. And this is possible, but at the cost of one mass distribution. But we can still do 3 mass distributions with 2 lines with one of them parallel. And something similar where one line has to go through a given point. Again, this is taking up 1 degree of freedom, so we need to use 1 mass distribution for that. So we can still do 3 mass distributions. Or we can even force both of them to go through a given point, and then we need to use 2 of these mass distributions, so we're only left with 2 mass distributions that we can do this way. And also, it's not hard to see that all of these results are tight, because you can always just place a bunch of points in general position, color them all with a different color, and then it's easy to see that you cannot do better because every line needs to pass, or through each point there needs to pass a line, and if they're in general position, that's the best you can do. Okay, so that's it. I want to thank you for your attention, and if there are any questions.
Thank you for this. We have time for 2 questions.
That last corollary of yours. So
Yes.
if the point is at infinity, then it's 2 parallel lines.
Yes.
I think that's the necklace theorem again.
So our proof actually doesn't really go through if the point is at infinity. That we had.
But at infinity, then I guess it's the necklace theorem. The points are sorted and colored.
Yeah.
And you're writing
Yes.
places.
Yes. Sure. Then you can just sort the point by. Yeah. Exactly. So that also works. Yes.
Did you consider, I guess, the version of this in 3D, which would be like the semi-transversal theorem, which is kind of the generalization of the ham sandwich, trying to be looking for a line as opposed to So in the 40s, there were 2 papers that have almost the same title. They were both called extension or generalization of the ham sandwich theorem. And they kind of interpolate between the ham sandwich theorem and center point theorem. And so in 3D, the statement is that you can find a line. So given, let's see if I get the numbers right. You have 2 measures in R3. Find a line such that any plane that contains that line gets you not equal cut, but like 1/3, 2/3 cut of each mass. I don't know if you guys.
So the short answer, no. We did not consider this, but it might be an interesting thing to
Just a comment that your second result, 3 math distributions, actually the first 2, I think were already shown
that is very well
in
possible.
2015 by Sergey Borek, Hurtado, Canton Foreman, a bunch of others.
Okay.
I can send you the reference.
That is, that would be cool. Thank you very much.
Any more questions?
Yeah. Does this apply for just circular shapes or any types of
Any type of shape. Yes. So we want that these measures are kind of nicely, so they should be measurable and things like that. So these measures should be in such a way that the measures behave continuously if we move these lines around, but that's not so hard to enforce. But apart from that, we can have any shape. So the pizzas do not need to be circular.
Thanks for